The very first lecture, which was in the other building, Osman, I gave a very broad introduction to black holes. Then we covered several topics. The first was basically space-time extensions. So coordinate singularities versus curvature or true singularities. Then last time we started with Schwarzschild, so global structure of Schwarzschild. And the basic point here is that for a long time there was a confusion about what whether r equal to 2m is a singularity or not, and we found that it is actually just a coordinate singularity. It is not a true singularity. And now what we want to understand is basically the global structure. What we want to understand is sort of the interplay between geometry and physics. In the Schwarzschild space-time. So this, of course, is a hallmark of general relativity, that there is a very nice interplay always between geometry and physics. Some things happen geometrically, they mean physically something, and physics then dictates also what space-time geometry is, and that's what we're going to do today. And we'll begin the fourth topic today, that is what is a black hole in general. So we are here, and these are the topics we want to consider. So what we saw last time was that we got a global extension, and therefore the space-time looks like u equal to 0. This is the classical coordinate u, and v equal to 0. These are the coordinates. In this region, big U times v is less than 0. In this region, big V times u is bigger than 0. In this region, uv is again less than 0. Here, uv is bigger than 0. And then we saw that we have singularities, and the singularities are given by r equal to 0. This is r equal to 0, and there are two lines, r equal to 0. And what we saw was that, in fact, the r is a perfectly well-defined function everywhere on space-time, and that it was given by this. It is given implicitly, however, in terms of u and v. We are u times v is equal to minus r upon 2n minus 1 times e to r upon 2n, the plus sign up here. So, and therefore the statement was that in this region uv is less than 0. So in this region uv is bigger than 0, so r equal to constant, this equal to constant. These lines are going to be space-like lines up here. That is what we saw last time. But also it's easy to do the coordinate transformation to see what happens to t. And last time I just indicated that t is actually singular here, and t is equal to little u plus little v upon 2. So these were the original u and v coordinates, not the classical one, not the rescaled ones. And then this just turns out to be equal to minus 2m times log of minus 4 m times u. And this is positive because u is always bigger than, is less than 0 here, plus log of 4 times m times v. And so you can see here clearly when u equal to 0, this is u up here, or when v equal to 0, this is u equal to 0, v equal to 0, t blows up, t becomes infinite up here. Right? So we see that there is a problem up here, which is what I was saying before. And nonetheless, the statement that I ended with by saying is that r equal to constant are perfectly well-defined lines. So r equal to constant lines were looking like this. This is r equal to r naught. And therefore, this is the, in the RT coordinates, this is the Killing vector field, d by dt. And similarly here, I got a Killing vector field, d by dt, d by dt. And then here it is path directed, d by dt. So this was the picture that we ended up with. And now we want to continue from here. Okay. So the first thing is that, yeah. So now we want to extract physics and from the geometry. So what we saw last time also, I think when we, or maybe we didn't see it, I don't know. The Killing vector field is d by u, so d by dt is a Killing vector field. So we saw that the originally, the metric in the region, so let's call these various regions, let's give them names. This region we'll call region 1. This region we'll call region 2, sorry, everything is getting crowded. This region is 3, this region we'll call region 4. And we started with our metric in the RQ coordinate, which are just dA squared equal to minus 1 minus 2m over r times dq squared, two-dimensional metric here, times dr squared upon 1 minus 2m over r. I can add the angular part up here, but that will give me the four-dimensional metric. The angular part is harmless, so we're not focusing on that. And therefore, our original metric was r bigger than 2m, so this was our original metric here. And it's manifest here that in this RT coordinate, d by dt is a Killing vector field. When I write d by dt, of course, anytime you write d by d something, you are implicitly assuming you know what the coordinates are. Otherwise, given t, I don't know what d by dt is. I need to know what is r and theta and phi, because those are the coordinates which are constant along d by dt. So here I'm assuming that when I write d by dt, I mean in this coordinate system rt. If I write d by du, I mean in the coordinate system uv. And this is going to be understood, but it's important to realize that. I mean, this is a very elementary calculus thing, but everybody makes mistakes at some stage. Don't think of d by dt. You have to say what coordinates you're using, basically. So t is not enough. I have to also say what the rest of the coordinates are. Okay. So here, when I say d by dt, I mean these coordinates. Okay. So we can see here immediately that d by dt becomes the norm of this Killing vector field vanishes, because one is norm of this Killing vector field. Let's call it, the Killing vector field is also called TA. So TA is equal to just minus 1 minus 2m over r. So this vanishes. So with this Killing vector field for r bigger than 2m, it's time-like, and then for r less than 2m, it becomes space-like up here. So we just started with one region, and now we get 4 regions up here by analytical continuation. And so we want to understand is really the interplay between geometry and physics. How do we interpret this space-time? Good. And what are its physical properties? Okay, so that's what we're going to do now. Any questions? Okay. So now let's continue. The first thing is that we saw last time already that how this Killing vector field looks like on the horizon. I think we wrote down explicitly its formula d by dt is equal to, let's get size wrong, is equal to 1 upon 4. d by dv. These are uppercase V minus u d by du. So again, let me draw the picture up here, same picture, but because there are too many things on that picture, so let me just look at this picture up here. So space-time is all the region with r positive. So this is r equal to 0. This is the r equal to 2m. again, R equal to constant is always U times V is constant, and that is why there are multiple solutions. U times V is constant has multiple solutions. So here we get R equal to 2m up here, R equal to 2m up here. So these two lines are R equal to 2m. Okay. So as R increases, so this is the patch we started with, so I'm focusing on this patch for a minute. That's where we start looking at the interplay between physics and geometry. So in this patch, we see that the Killing vector field is time-like. Our d by dt Killing vector field up here. It's time-like. Its norm is clearly negative because R is bigger than 2m, so this is less than 1. And therefore, the norm is clearly negative up here. Therefore, this is the picture that we're getting up here. And this is the region 1 that we are focusing on. We started out with region 1, and that is what we are focusing on here. Okay. So, as R goes to infinity, maybe I should write down the full metric just for the sake of completeness. So this is the angular coordinates up here. As R goes to infinity, clearly these terms become negligible, and therefore the metric looks like Minkowski metric. So there's no problem. So if you go up here in this direction, the metric tends to Minkowski metric. So the metric is, therefore the space-time is clearly asymptotically flat. There's no problem about that. And therefore at infinity, this d by dt Killing vector field, ta, the norm of this just goes to -1, because norm is just equal to 2m upon r goes to infinity, goes to -1. Therefore at infinity, here as I was saying last time, the Killing vector field just looks like the Minkowski time translation, which is very different from a boost Killing vector infinity. But near the horizon, the Killing vector field looks like the Minkowski space boost Killing vector field. So what we're doing always is the following. In general relativity, we're always combining two things. We're combining gravity, which comes from Newtonian theory, and we're combining spatial relativity. The only consistent, in order to do it consistently, we are led to the general relativity. There are also other consistent relativistic gravitation theory, but here we're focusing on general relativity. So therefore, a lot of our intuition comes from Newtonian gravity on one hand and general relativity on the other hand. But we should not take this intuition for granted. We should not think of what we think about in Newtonian physics or in spatial relativity is the same. So here we see a difference. Namely, the Killing vector field looks like a time translation here and looks like a boost near the horizon up here, right? So this is where it's not true that the Killing vector fields in curved space-time will look like Killing vector fields in Minkowski space-time globally. They can interpolate like that precisely because there is curvature in between. Okay. So far so good? Now the statement is that therefore as we are coming in, the curvature is growing. And how is the curvature growing? So I wrote down last time, one curvature invariant that is most useful is this Kretschmann scalar. And that Kretschmann scalar is given by just RABCD. This is a four-dimensional Riemann tensor, RABCD. So as a measure of curvature, what we can look at is square root of the Kretschmann scalar up here. And then the statement was that this actually goes like Gn upon R cube times C. This has dimensions of radius, and therefore this the Riemann tensor, it has dimensions of 1 upon length squared, which is what it is. So that's what the Kretschmann scalar looks like. And of course, the difference is, of course, that the horizon structure is what distinguishes Minkowski space and this black hole solution. So it is really the fact that Kretschmann scalar is 0 in Minkowski space-time and is not 0 in this space-time, which is allowing us to do this kind of, which is allowing the space-time to do this kind of interpolation. So let us understand this Kretschmann scalar a little bit better, right? What does this Kretschmann scalar mean and what does it look like? So what we can do is the following. To get physical feeling, now we're comparing with Newtonian physics with general relativity, we can calculate what the Kretschmann scalar is here, the surface of Earth. Right? How much is curvature here? So we can calculate that. and we can calculate it on the horizon. Say, for example, for a solar mass black hole, and we can compare. And we can see, did something dramatic happen, or something, nothing much happened. So we can do that, and then if you calculate the Kretschmann scalar on Earth, so square root of k on Earth, so E is for Earth up here. So that just turns out to be about, you just put the numbers in up here, I mean, radius of Earth, mass of Earth, and RC squared, C squared up here. And then we'll just get this to be about 1.5. I just use some units, which is not, I could have used meter squared, but that doesn't make any difference because we're just going to look at ratios. So it's about 10 to the minus 17 kilometer minus 2. And we physically know that this curvature is very small, right? I mean, for all practical purposes, we take space-time to the flat space-time. When in CERN, when they do experiments, they don't worry about curvature of Earth very much. And so they just have to, we just think of metric as being flat metric. And that is because that's on the surface of Earth, this is the curvature. What about the Kretschmann scalar on a solar mass, one solar mass black hole? So this was Earth, this is one solar mass black hole. So, you just take a star of the size of sun, mass of sun, and you collapse it. When you collapse it to become a black hole, we'll have to take the mass of sun, which is about 10 to the 33 grams, and we'll have to compress it into a radius about 3 kilometers. Schwarzschild radius of sun is about 3 kilometers, so the horizon is at 3 kilometers up here. So the question is, what is this at, let me actually say, so this is one solar mass black hole, and we're calculating this at the horizon. So here we looked at the surface of Earth, so we can look at the horizon up here. And we find this to be equal to 1.1 times 10 to the minus 1. So we can see that the ratio of square root of k on Earth and square root of k on one solar mass black hole surface. So I'm heuristically thinking of the surface of black hole to be the horizon. Okay. So how much is it? I mean, it's huge, right? It's 1.5 into 10 to the 16. It's about 10 to the 16. 1.5. You already divide those things, so it's about 10 to the 16. And it is huge. And this is what you would expect, that the curvature is really huge at the horizon. This is what our intuition tells us. But wait. At the horizon, so if I got a black hole, and if I want to take curvature, Kretschmann scalar, I can calculate Kretschmann scalar by, if you like, itself rather than taking its square root. The reason I'm looking at square root is that the tidal force is given by not the square of Riemann tensor, but the Riemann tensor itself. So this is a measure of tidal force. How much you are going to rip it apart if you are on surface of Earth, because this part of my body, this point of my body is going towards the Earth up here, to the center of the Earth. This is going to the center of the Earth. And if you look at the tidal force, then there is actually a force between them, just not because of the mass here and mass here, but just because the gravitational field of Earth is not uniform. And there is a small tidal force up here, and the measure of that tidal force is this. Now, and the measure of that tidal force on the black hole is this, it's 10 to the 16, and that is why if I were to fall in, then at the surface of the black hole, I will be completely torn apart. The tidal force is just too big to really to tear me apart. But look at this thing. What is this? For a black hole, this square root of this quantity up here is just given by Gn, but R is equal to 2m, right? R is equal to 2m on the surface of the Earth. So let me just, when we say R equal to 2m, I again mean R equal to 2Gm upon C squared, right? Because I'm just, most of the time I'm not putting G and C up here, I put them here so that you can actually do the calculation yourself, substitute the value of G and see that this is true. But so when I do that, on the surface of the black hole, this really goes like m cubed, this really goes like m, so therefore this goes like 1 upon m squared. So at the horizon, in fact, the Kretschmann scalar, the tidal force, goes like 1 upon the mass of the black hole whole squared. Now we know that there are black holes which are supermassive in the center of galaxies. They are about 10 to the 9 solar masses. So if I got a black hole, which is supermassive black hole, so if I calculate this same quantity, square root of k, of at the horizon for 10 to the 9 solar masses, you calculate how much it is, and it is about it is about less than on Earth. I didn't write down the precise value, so let me just say it here. It is about, so this is about 0.73 times square root of k on Earth. So you have got this supermassive black hole and you're falling through the horizon. For this supermassive black hole, regarded as an isolated system, it has all these miracles are still true. That at infinity, the Killing vector field looks like time-like. And near the horizon, the Killing vector field, it looks a little bit like boost. And on the horizon itself, it becomes null. All those things are still true. And yet, the tidal force that I will experience on the surface of a supermassive black hole is less than that on Earth. So I would not feel anything if I'm falling through this black hole. The tidal force will be completely negligible. I will not be torn apart at all. It's very counterintuitive, and it's very important to realize that the tidal force is not a measure of where the horizon is. Horizon is an elusive thing, as we are going to see more and more and more, and that is what often raises all kinds of paradoxes or surprises in people's thinking about, in particular when you go to quantum mechanical properties of black holes. So the horizon is really elusive. It's sort of, it's a sophisticated, complicated thing. At the surface of the horizon, the curvature can be very, very small, much smaller than that on the surface of black hole. So I would feel nothing at all, but of course the global geometry is very different. And now what we are going to see is, well, what happens here? What is the difference then? If I'm just passing near Earth, or I'm passing near this supermassive black hole, what is the difference up here? Well, the difference is the causal structure. In Minkowski space, the causal structure is such that the light cones are always just future pointing. Okay, so difference is in the causal structure. So in Minkowski space, for example, if I take this Minkowski space, I can take this origin up here, and of course this is just the light core of the origin. This is the origin. This is Minkowski space. And here, the statement is that so again, I'm looking at RT plane. I will draw another picture in a minute. I'm just looking at the RT plane. And this is any random point in the Minkowski space. There's no particular meaning to this. I just choose one. And then the statement is that I got these light cones, and the light cones everywhere in the Minkowski space are just 45 degrees. So there's always light which goes outward, light ray which goes outward or inward. So we've got these two kinds of light rays. Now I want to sort of emphasize this a little bit better, because at this stage I don't need it, but I'm going to need it in 2 lectures. So let us understand what I mean by this. So because this is really a point, this is really a 2-sphere, because I'm just looking at RT plane, so every point up here is a 2-sphere, except that origin is taken to be a point, so it's always confusing a little bit. But this is all 2 spheres up here, every point. So what do I mean by it? So let's just draw 2 spheres. I cannot write a 2-sphere. I cannot draw a 4-dimensional space-time diagram, so I will draw it as a circle. So supposing I take this circle up here, and actually supposing we actually are going to look at light rays which are emitted, right? So supposing I take a light bulb, we don't have a light bulb in this room, but supposing I have a light bulb which is spherical symmetric, and I just light it instantaneously. What will happen? In this room, light will propagate outward, and light will propagate inward. It propagates in both those directions. Light fronts which propagate outward are growing. Light fronts which are propagating inwards are shrinking. So that is what is happening up here. So the statement up here is that I'm going to get light fronts which are propagating outward. Their area is going to be increasing. So these are light rays. These are all light rays. So these are all light rays in the Minkowski space. This is the depiction of a two-dimensional sphere, light rays, light arc. And then I got the other kind of light rays, the other light rays, which are going inside. And they are going inside like that. They're shrinking up here. So you can see that light front here is expanding from here to here to here. As time passes, it's expanding. And this light front is contracting. So this light ray up here is inward going. And this light ray is outward. And if I'm in Minkowski space and I got this light ray going out, then the outward going light rays are just going to go out to infinity. And that is why I can see you. If you're not a light source of light, but you're reflecting light, so for me it is a reflective light, because the light front up here is going out, and I can be very far away and I will still be able to see you, because light from you is causally coming to me. Right? But what happens to the black hole is the following. Then again, I can look at the light rays, and I can look at light rays up here. So this outgoing one is this outgoing light ray here. So this is really, this whole pencil of light rays is being represented here by this outgoing light ray, by outgoing ray up here, because each point up here is a two-sphere. So this is a two-sphere, this is two-sphere. R is increasing here. Because R is increasing, this light front is growing, and here R is decreasing. And this is, if you like, maybe in the older, so this is the yellow light front that is going inside. Okay. So what we're doing here is each point up here is a two-sphere. Each point is a two-sphere up here. This point is a two-sphere. Light rays are going, and so this picture is the same as this picture. I just want to emphasize that. It looks like a single light ray, but it really is representing, because I'm in the RT plane, in space-time, it is representing three-dimensional surface rather than a one-dimensional line, because each point is a two-sphere. So what do the light rays look like here? So here, the light rays, they can be outgoing light ray, and they can be ingoing light ray. So, sorry, we should use the same notation up here. The incoming one is yellow. So this is ingoing light front, and this is outgoing light. Again, each point here is a two-sphere, so it really is a picture like that, but it is being depicted. Each point is just being, we're factoring out by the two-sphere, and that is why it looks like a one ray going out and one ray going up here. Okay. Then what happens here, however, inside the black hole? Well, we're going to see this more detail, but I just want to give the introduction. Namely, here I also have the outgoing light ray, and I also have the ingoing light ray. But you can see that both of these outgoing and incoming light rays, the outgoing here, R is increasing and this is decreasing. That they will end up on the singularity. Here, the outgoing light ray goes out to infinity, and therefore I can see this point. If light is emitted from this point, I can see to it. Distant observers can see it. Whereas here, I cannot see it at all. And this is the first heuristic reason, if you like, not heuristic, but this is the first intuitive reason why this region, what we call region 2, is called black hole region. What we had up here, the region 1, is asymptotic region. It is connected to infinity. And we get a black hole region up here. Now, but the extension didn't stop with this black hole. The extension continued us on the other side. And again here, in this region, again, if you just look at the U and V coordinates and invert using these, you will find that R is going to infinity here, in this direction. just as r was going to infinity in this direction. And again, we get asymptotic flatness here. So you go out in this region 3 now we're looking at. This region 3 is also, it's an asymptotic region, we're going back. So somehow the extension gave us, we started with one asymptotic region and the extension says, no, there's also another asymptotic region. We're going to see just in a few minutes that this is only mathematical description. In physical space-time, in physical situations, if a black hole actually forms, this region is not really relevant. But in the critical space-time, as a mathematical description of the black hole, which is static, Schwarzschild black hole, this region is important. We're going to see all these things. I know that there's a big mixture of audience here, some who are super experts, some who have never seen these things before, so I'm trying to do a balance between the two. And if I go back to, go further to this region 4 now, region 4, then again, what I obtain is the following. So region 4 here. Here, in the asymptotic region, and the same thing is true here, I'm just not drawing it, not to crowd the picture. You got outgoing rays, which go out to infinity. You have got incoming rays, which will go and fall into the black hole. In this case, the outgoing and incoming rays both fall into the singularity. Therefore, this point is invisible from inside. In this case, what is happening is really the time reflection of this. Namely, if I take this point, here we're looking at a light. I got a 2 sphere, and I light it instantaneously, and the light rays or light waves actually goes out to infinity and come into infinity up here. But I could do the opposite. I could do the time reversal of this. Instead of looking at outgoing rays up here, future directed rays, I can look at light rays which are actually converging. In other words, at any point, I got future light cone, and I can also look at the past light cone. And the future light cone, future light rays are leaving this point, and the past light cone, light rays are arriving at this point. So I can look at the past light cone, which I haven't done so far. If I looked at past light cone here, the past light cone will, the rays from past light cone from here will come in this region, will go in this region. Now here, however, what happens is that the rays from the past light cone, the outgoing ones are going here and incoming. So this is the past. This is not physically interesting because this is not causally. Causally what is happening is that if I light here, rays are going in the future direction, not in the past direction. But nonetheless, just for understanding these two regions, whatever is happening to the future directed light rays here is happening to the past directed light rays here. However, if I look at now the future directed light rays, which is what we were doing before, these are future directed outgoing, and these are future directed ingoing. And what we see is that the future directed light rays can enter in the asymptotic region and also can enter in this asymptotic region. So the point is that all the points in this region are invisible for region 1 and 2. All the future directed light rays are going to come up here, whereas this singularity is visible both to region 1 and region 3 up here, both is asymptotic region, and so it is opposite of black hole singularity, and that is why it is called the white hole singularity. So this is a white hole singularity. So this is a geometrical picture of space-time, and suddenly we're getting physical interpretation. This singularity should be thought of as a black hole singularity, in the sense that it is all invisible, whereas this is completely visible from outside. Here the future directed null rays are all going in this region, are all falling into the black hole. Here the past directed null rays, which are mathematical construction we can do, are all falling into the white hole, but the future directed ones are going down. So this is a singularity which we can see. If this existed, we would be able to see it, and it would have terrible consequences, and therefore normally in physics we think, in classical general relativity, the statement is that this singularity of this kind are not physical. In classical general relativity, the singularities of this kind would not be formed starting with normal matter. And the general belief is that singularities of this kind really don't exist in our universe. But there's no proof of this. This is a general conjecture on which everything is based, and everything so far is consistent. So we continue to work with this hypothesis that these singularities are unphysical. These singularities, on the other hand, are not unphysical in form. So this is the zeroth order, broad brush understanding of geometry and physics up here. Namely, this is a black hole singularity. This is a white hole singularity. I got these two asymptotic regions. And these are the properties, mathematical properties, of the Kruskal extension. This is a separate question whether this kind of object exists in our physical universe. That's a separate question. Can we form such an object? That's a separate question. Here we just ask understanding the mathematically, supposing somebody gives us this, then what are the physical properties of this particular extension? That is what we're looking at the moment. Any questions? Okay. So, how many people think this is all going too slowly and too elementary? The advanced people know it, but I know that polite, they're not raising their hands. Okay, good. So now we're going to delve more detailed properties. We're going to come back to all these things in a little bit, a couple of times. But at the moment, just the first impression of what the interpretation of this space-time is. So now what we want to extract more and more physics from geometry. And so the next thing that we're going to do is the order which is more pedagogical. So let me follow that order. The next thing that we're going to do is geodesics. So the second topic that we're going to do is geodesics. So geodesics just follow this equation. And from this equation, it follows immediately that eta dot eta, the norm of this vector field, is constant along geodesic. And therefore we got two kinds of geodesics. Well, there are three kinds of geodesics. They can be space-like, time-like, or null. But physically we are most interested in time-like and null ones. I'm not saying that there's a theorem which says that space-like don't exist or so. I have no physical interpretation, but so far we haven't found good physical meaning for these quantities. So therefore, these are either say time-like, when eta dot eta is less than 0, and null, when eta dot eta is bigger than 0. And then there is also space-like, right? When eta dot eta is bigger than 0. But those will be tachyons, and we haven't seen any evidence for tachyons, so we don't discuss them in very great detail. So I got these two kinds of geodesics. And now, the important thing is that in this Schwarzschild space-time, we got Killing vector fields. So the Killing vector fields can be time-like, which is d by dt. And there are three rotations because it's spherical symmetric space-time, right here. Though everything just depends on r, so it's spherical symmetric, and therefore there are three rotations. We call them, people call them phi I. Three rotations. So rotations along x-axis, y-axis, z-axis. There are three independent rotations of Killing vector fields. But these three rotations, of course, they are tangential. To r equal to constant to spheres. So they are linearly dependent. They are not independent. There are three vector fields. They are independent as Killing vector fields, but they are all tangential to two surfaces. So as ordinary vector fields, not as Killing vector fields, as ordinary vector fields. In other words, one of them can be expressed as a linear combination of the other two, but those coefficients are going to be functions, and that is why the statement, as Killing vector fields, they're independent, they're not constants. If you have got two Killing vector fields, the sum or the linear combination is a Killing vector field only if the coefficients are constant. So as Killing vector fields, they're independent, but as vector fields, they are actually they span only a 2 surface and not a 3 surface. But anyway, we've got these 4 Killing vector fields, and the point is that these Killing vector fields represent symmetries. Time translation means TA, the time-like Killing vector field, is a static or Killing vector field. So you've got time translation symmetry, and you all know from the fundamental physics that if you've got time translation symmetry, then there's a conserved quantity which we typically interpret as energy. And if you've got 3 rotations, then we know that we've got conserved quantities which we represent as x, y, z directional angular momentum. So the statement is that if you have test particles which are represented by geodesics, so these geodesics represent test particles. So if you have got geodesics which are test particles up here, then the statement is that that along the moving of those test particles, by test particles we mean that we're ignoring the effect of the particle on the geometry. So for example, when we calculate the orbit of Earth around Sun, we think of Earth as a test particle in ordinary Newtonian gravity, and Sun as producing the gravitational field, and how does Earth move in that gravitational field. So we're doing the same thing up here. Those test particles are now represented by geodesics. So the orbit of the Earth around the Sun would be a geodesic in the Schwarzschild space-time. In this asymptotic region up here, it's a geodesic. All right. Then the statement is that there is a constant quantity, as you would expect. So given any Killing vector field, I can take eta A grad A of KB eta B. You expand this out, and you of course find eta A grad A eta B. So KB comes out, and I get eta A grad A eta B plus eta A eta B grad A KB. And we see here that because of geodesic equation, this is 0. And this is actually symmetric. Eta A, eta B is symmetric, therefore this is symmetrized. And therefore this object is just 1/2 of the derivative of K of the metric. If you just expand this derivative out, you will get this to be the answer. And this is 0, just because it is a Killing vector field. By Killing vector field, we just mean that we mean Vk of GAB equal to 0. Therefore, this is also 0. And therefore, this quantity is conserved. So therefore, the scalar product between the tangent vector to the geodesic, the 4 velocity of the particle, if you like, and K is actually conserved. And as I said, typically, for time like geodesics, we regard this as being the energy of the particle, and we regard these as, for the rotations, we regard these as being the angular momentum of the particle. But then something very interesting happens for null geodesics. So supposing we got in this region 1 up here, and we have a particle in region 1, we have a point, and supposing I'm looking at the light ray emitted from this point. So I have a point up here, point 1, point 2 in space-time, point 1 and point 2 in space-time. And light ray is propagating up here. So this is eta A grad A eta B equal to 0. This is null geodesic between 1 and 2 that I happen to be looking at. Well, at every point there, I've got a Killing vector field d by dt, or let's call it this TA. I've got a Killing vector field here, TA. Now let us consider object or observer who is stationary with respect to the black hole. So its r or theta and phi coordinates are not changing. Therefore, the observer is moving along the integral curve of the Killing vector field. So we're just moving around the integral curve of this Killing vector field up here. Well, if that is the case, we're moving along the integral curve up here, then the statement is that the forward velocity of the observer, of a stationary observer, of a static observer following the Killing vector field, is tau A. So it is going to be proportional to the Killing vector field. But forward velocity of the observers is always unit, so I have to divide by the norm of the Killing vector field. Now Minkowski space, this doesn't matter so much because t dot t is equal to -1, therefore this is 1, and therefore I don't care about this factor. But now it matters because we just saw that t dot t is exactly equal to -1 minus 2 over r. So this is just going to be equal to dA divided by 1 minus 2 over r. We're looking at this null geodesics in the asymptotic region outside the black hole. But what we just saw was that TA is a Killing vector field. So TA, and I got eta A times TA, is a constant of motion. This quantity, eta A times TA, is constant of motion. On the other hand, because I got observer, that observer is going to, I can take the scalar product between the forward velocity of the observer and the geodesic. So this is geodesic, and this is the forward velocity of the observer, which is unit. And from special relativity, we know that this is what we mean by frequency. Light ray, which is tangential to eta. We got geodesic up here, light ray. And therefore we see here immediately that there is an issue, there's a problem that we have to look at. Namely, that we see that this frequency is going to change as I go from here to here, because this is constant, but frequency is t dot eta, and r changes when I go from here to here. So at this point I got some R1, at this time I got this R2. Therefore the frequency, nu1 upon nu2, is just given by tau A eta A into 1, tau A eta A into 2. And that is just given by this, and therefore we can see that this I can write it as t upon 1 minus 2 over r. So I'll get TA eta A, TA eta A, but that is constant, therefore this is just going to be equal to 1 minus 2m upon R2 upon 1 minus 2. Now R2 is bigger than R1, therefore this quantity is smaller, and therefore this quantity is actually bigger than 1. So we see that actually the frequency of the observer at nu1, or the frequency of light ray as measured by the static observer at nu1, is going to be bigger than that at this point up here, which means that the wavelength which is equal to the speed of light divided by the frequency is going to do the opposite, namely lambda 1 up here is going to be smaller, or lambda 2 is bigger than lambda 1. So the wavelength is actually increasing, or the frequency is actually decreasing, which means that there is a redshift. Redshift just means that the frequency is decreasing or the wavelength is actually increasing. Light seen by this observer has larger wavelength than light seen by this observer. It's the same light ray that is going in, and that is just because in between in the space-time is time dependent. The norm of the Killing vector field is sorry, space-time is not time dependent because space-time is curved and the norm of the Killing vector field actually depends on the value of R up here. So this is the important thing. Now, this is a small subtle point that I want to tell you because people make this mistake very often. Namely, we know that for an ordinary particle, for a massive particle, this really is the energy. This T dot eta would be the energy, as I just told you. So people think that, well, here is a light ray. Light ray is a photon. So this is a world line of a light ray. This is a world line of a photon. So this typical statement that people often confuse with is the following. They would just say that I would say energy is conserved. Along geodesics. But null geodesics is a trajectory of a photon. And energy of a photon is just h nu. Put these three things together, so you would obtain this result that h nu1 should be equal to h nu2. H is the Planck's constant, and therefore nu1 should be equal to nu2. And we see this is not the case at all. The frequency actually is redshifted. There's no question about it. The frequency is redshifted. This is a wrong reasoning. It seems very logical, very simple up here. But the point is that null geodesics should not be thought of as a trajectory of a quantum particle, which is photon is a quantum particle up here. So nu1 is not equal to nu2. This is a fact that nu1 is not equal to nu2. This is something that is observed right a long time ago. This is one of the classic tests of general relativity, and so we should just not use this reasoning up here, namely that something that is perfectly fine for the time-like geodesics or massive particles, but we should not apply it to this reasoning to the photons. That is just incorrect. So I think one should not look at the geodesic trajectory of a photon, and perhaps we should not think of. So the question is then, what is the real thing that what should we be really doing up here? What does this nu represent? This frequency I define up here, which I define to be equal to eta tau a, the inner product between the, sorry, I should have put a minus sign up here. The frequency is, they are both time-like vectors, therefore that is actually a negative quantity, so frequency is positive, so we just put it's just like for energy, we always put a negative sign, because our convention is energy is positive. So nu is equal to tau a is equal to pi 8 minus tau a time. And so the question is, what is the origin of this? The origin of this is really coming from geometric optics approximation. Of solutions to Maxwell's equations. This frequency notion is really coming from classical Maxwell fields, and we're looking at geometric optics approximation. Again, it's something that I could do in half an hour, but it's too much of a digression. This approximation is such that we're thinking that the amplitude is slowly varying function, and the frequency is large compared to the curvature scale. So frequencies, or if you like, the wavelength is small compared to the curvature scale. The curvature radius is much larger than the wavelength. Under those conditions, Maxwell's equation is plug in Maxwell's equation, assuming there are solutions of this type, and you will find that in fact this is the correct notion of frequency that is coming in from the frequency in the solutions to Maxwell's equation that we all know and know. So this is a kind of small conceptual point that I wanted to clarify. Now the last thing that I want to do is a couple of two other things, and then we'll be done with the third part, which is geometry and physics of Schwarzschild space-time. And so the statement up here is that there is also for fields, we also have conserved quantities with Killing vector fields. So fields also we have got conserved quantities also with Killing vector fields. And the reason is because if you have got a field, like Maxwell field or scalar field, we're going to stress any tensor of that field. Now this could be causing the gravitational field. So this is completely general. So this is not restricted to Schwarzschild space-time. If you have got a space-time with a Killing vector field, then the statement is that we've got conserved quantities. So I can take a field. This field could be the source of the gravitational field via Einstein's equation, or it could be a test particle, like for the geodesics. So it could be either test or it could be source, which is producing the curved space-time. But we know that this is satisfies the conservation law, where grad is a derivative operator as usual, compatible with the metric. Simplicity, we're always looking at torsion-free derivative operators. So grad of TAB equal to 0. That is the condition the stationary tensor satisfies. And therefore, if I define a coordinate quantity J to be equal to TAB times KB, then we find that grad AJA, which is equal to grad A TAB, KB, and that is just grad A TAB, which is 0, and then again I get here grad AB TAB times grad A KB. But this is symmetric, therefore this is automatically symmetrized, like this, free of charge, and this quantity is just again lead derivative, 1/2 lead derivative of the metric with respect to that Killing vector field, and therefore this is also 0. And therefore this, we're going to conserve current, and therefore if I'm given a space-time in which I got two hypersurfaces, sigma 1 and sigma 2, and supposing they go out to infinity, just for a second, second argument, just for a second. If they go out to infinity, if they have a boundary, then you have to worry about the boundary. But if they have a boundary, in any case, whether they have a boundary or not, we know then that this is divergence free. Therefore, the integral of JA, flux of JA across sigma 1 plus this quantity, plus this quantity, plus this quantity will be 0 with appropriate orientation. If in fact we assume that these boundaries are at infinity, the surface actually goes out to infinity, then, and we assume that TAB goes to 0 at infinity. So assume that the stationary tensor, the fields actually die at infinity, which is typically a good approximation, a good assumption. And then the statement is that in that case, we find that if I take integral along sigma 1 of TAB times KB, so that is a J. And if I integrate it along that surface, so I take a unit normal to that surface, let's call it tau. So tau A is the unit normal up here. In this Stokes law, I have to take outward normal. So if I take the outward normal, I would find that the integral here plus the integral here is 0, but we just keep the future directed normal always, in which case we find that this minus integral, this minus sign just comes because I'm using here t to be inwards, t to be outward of here, times TAB, KB times A. Sigma 1 minus sigma 2, that is equal to 0. So I got a conserved quantity, namely this quantity is conserved. So if you have Killing vector fields, you get conserved quantities associated with geodesics. So for test particles, you get conserved quantities associated with the fields, whether they are test or they actually are source of gravitational field. You got this nice conserved quantities. And again, if the Killing vector field k is time-like, we call this conserved quantity energy. Otherwise, if it is rotations, we call it angular momentum. And finally, you have got the homework, the first homework, which is due next Monday, a week from today. And that homework has the following thing. That in fact, if you have got a Killing vector field, if you have symmetry, you can define not only conserved quantities for test particles and for fields living on that space-time, but you can define conserved quantities of the whole space-time as a whole, if you like, of the space-time itself. So again, Killing vector fields defined. And these are called covariant integrals. But whereas these conserved quantities just exist in any given space-time, these conserved quantities exist only in the vacuum region. In other words, where Einstein tensor is equal to 0, or the Ricci tensor is equal to 0. Equivalently, Ricci tensor is equal to 0. So in that case, the statement is that, for example, you may have a star. So you may have a star. So this is space-time diagram of a star. This is the world tube of a star. So at any given time, star is a ball, and that ball is represented by this disk up here. There's a ball. So this will be instead of time, this is t equal to constant. And you've got this ball up here. And the statement is that what I can do is I can consider a two-sphere which is surrounding the source. So this is in the vacuum region, as we want. And the statement is that in this vacuum region, we get a nice conserved quantity. So what is a conserved quantity in this vacuum region? So the homework asks you to show that if I take a Killing vector field and consider this quantity, we saw that the symmetric derivative is identically 0. Therefore, the statement is that if I take the derivative, that derivative is just equal to its antisymmetric part, because its symmetric part is 0. Right? Because symmetric part is 0. This is Killing vector field. Then this is already antisymmetric. So it's a two form. So we just introduce a notation called FAB. Just call it FAB because it's a two form. It's just an antisymmetric test. It's a two form. So we just introduce a notation up here. And then the homework tells you, gives you an identity. For extra credit, you can prove that identity, which says that if Ricci tensor equal to 0, then these two forms satisfies, of course, by construction it satisfies that f is curve free, because it's already a curve of one something. And then this is trivial, but if RAB equal to 0, then it is also divergence. Now you will immediately recognize that that's why I call it F. This is exactly Maxwell's equations. So the statement is that these two forms satisfies Maxwell's equations outside sources. Now you all know that if you have Maxwell's equation outside sources, you can define a charge. Namely, I can take, if this is a fictitious Maxwell field, so therefore this FAB is a mathematical Maxwell field. There's no real electric charge there or something, but mathematically, it has properties of Maxwell field. It satisfies the same equations as Maxwell field. Therefore, we can apply the same mathematics that we use for Maxwell equations, and then we can say that, well, I'm going to get a charge up here associated with this Maxwell field, and then the charge associated with the Maxwell field, as you all know, is just given by the charge associated with the Maxwell field. This Maxwell field is constructed out of the Killing vector field K, so therefore I call it Q. So this I call it charge because it's a mathematical charge. E just given by 1 upon 4 pi times, those of you know how to integrate two forms. You can just integrate this star FAB, that is the charge. Or from elementary physics, we know, so this is around that S2 that we got here. Or this is the same as construct the electric field out of that Maxwell field. Take a unit normal. So take the unit normal to the two sphere in this slice. To construct the electric field, I need to introduce a rest frame. I need to introduce a T equal to constant surface. And then you take R to be the unit normal. Just write like that. Unit normal to this two sphere within the slice. And then two-dimensional volume integral of that slice. So in Schwarzschild space-time, this two-dimensional volume integral, if you take a two sphere, it's just trivial. It's just equal to r squared sine theta, d theta d phi. If you take the round two sphere, that is r equal to constant and t equal to constant to sphere. If you take that to sphere, then this is equal to that, so you just calculate that. And if you did this for k equal to t, what you obtain is precisely the mass. So if you like, the charge, the electric charge of this fictitious Maxwell field constructed of the Killing vector field is just the mass of the space-time. And similarly, if it were one of the rotations, then it would be the angular momentum of space-time. Again, for experts, I should say that there's a factor of 2 that you have to smuggle in to get angular momentum definition, which is compatible with what we define at infinity, but this is angular momentum space. So this is in the Maxwell case, this would be the mass, m is m up here, and these will be just 0. So the homework problem asked you to calculate these quantities for a space-time. So therefore, this is what is happening with the Maxwell with the Schwarzschild geometry. So I completed the interplay between geometry and physics, because you see, this is a beautiful example. Again, all are beautiful examples, but this is a very good example in which I got a Killing vector field, which is geometric symmetry, it's an isometry, and if you have got a Killing vector field, then you can actually define the physical quantities like mass and angular momentum if you have got vacuum equations. So this is the end of this third part, and next time we'll start asking the general question: what is a black hole? We know in Schwarzschild I motivated that this should be thought of as a black hole region, and this should be thought of as a white hole region. But we would like to know that are all fine for Schwarzschild spacetime. But what do you mean by a black hole? And that's what we'll do in the next lecture. What is a black hole in general? Good. Thank you. And again, the homework is due on Monday, but my office hours are on Friday. But if you want to stop by after either Monday or Wednesday classes, please feel free to do so.